So if you recall last time, we'd begun to talk about parallel streams. We've talked quite a bit about sequential streams, enough so that the grad students should be able to do the streamish portions of the fork join pool. Now we're going to talk about parallel streams. After we finish the second portion of assignment 2, we're going to go on and redo the program that we've just been doing, except we'll use streams all the way through, and you'll see it's much simpler when all is said and done. So what can parallel streams get us? Well, we talked before about how parallel streams are almost identical to sequential streams. They just say parallel stream, not sequential stream. We also talked about a little bit about the internals of what's happening under the hood with parallel streams. And now what we're going to do is give an example. And the example we're going to look at is going to be the SearchStream example we had before, except this time, rather than using a sequential stream, which took about 2,000 milliseconds to run, we're going to do the parallel streams version, which took only 437-ish seconds. Obviously, it's every time you run this, you get a slightly different result, but that's basically the idea. So this particular example uses the SearchWithParallelStream class, which is this guy. And as before, it's got two methods, processStream and processInput. Here's the way to remember the differences between these methods. So processStream, for all the examples we look at, is going to essentially get input, which will be an array or an array list of strings where each string contains the text for a work of Shakespeare. So that's what processStream gets. So you have a list of strings. And then for each string, for each work of Shakespeare, we're going to call processInput. And processInput is going to go ahead and take a list of phrases and go look up in that input string to find whether those phrases match in that string. So for each string, we take it and we look for a list of phrases in each string. So you can kind of think of it as like a big kind of two-dimensional array, if you will. And we're going to see here that unlike before where we use stream, this time we're going to use parallel stream to run the list of works of Shakespeare in parallel. And then for every work of Shakespeare, we're going to search for the list of phrases in parallel. So it's going to be parallel in 2 dimensions. But otherwise, the code is going to be almost identical. The other thing to note here is we're reusing map, collect, filter, and so on, more or less identically from what we had done before. So here's processStream. This is the thing that uses a parallel stream to search a list of input strings, 1 string for every work of Shakespeare, in multiple threads. And as I said before, each string has a work of Shakespeare. And then we'll use processInput, and that uses a parallel stream to search each input string and locate all occurrences of phrases, also in multiple threads. And when I say multiple threads, what I really mean here are multiple worker threads which will be running in the common fork join pool. Remember that the fork join pool, there's a common fork join pool shared by all the parallel streams within a process. And that common fork join pool has a pool of worker threads, starting out typically to be the number of cores, and which you could change if you need to, but for this case, we're just going to take the default because these are essentially compute-bound jobs. We're not doing I/O. We're just looking in the strings that we've already initialized with the works of Shakespeare. And so in that case, we're going to use the threads out of the common fork join pool to do the work. That's all under the hood. You don't have to program to the common fork join pool. That's handled for you by the Streams framework, unlike your programming assignment number 2, where you're explicitly programming the fork join pool. OK, so let's visualize this. It's going to look almost identical to what we saw before. For the sequential version, we take a list of input strings, 1 string for each work of Shakespeare. And when parallel stream is called, it's a factory method that converts that list collection into a parallel stream. And what that means is you've got a bunch of substreams with chunks of input strings. And that decomposition process continues essentially until you have a single string. And that single string will then be handed off internally to the fork join pool to do its thing. The output of this is a stream of input strings. And that stream of input strings is then connected to the map method. Remember, map is an intermediate operation, a so-called higher order function, and it takes a behavior as its parameter. And what it's going to do here is it's going to call processInput, which is its behavior, and processInput will then search for the phrases in a given input string in a given work of Shakespeare in parallel. So now we've got parallelism going in 2 dimensions, parallelism across the input strings, and then parallelism across the phrases we're searching for as well. And I'll show you that when we look at processInput in more detail. The output of map will be a stream of lists of search results. So again, for every phrase that we find in our input string, we are going to, or for every phrase that we have, we're going to create a result, which will be the list of search results. And that will then be collected. Collect will trigger all the intermediate processing, pulling things through the linked list of processing operations like map and so on. And then it'll convert the results into a list. Now, processInput returns a list of search results, so collect will return a list of search results. And that list of search results will be based on, the order of the list of search results will be based on encounter order. And all encounter order means here is that whatever order the works of Shakespeare were ordered in the original input list will be the same order that things come back when all is said and done at the end. So if it was Hamlet followed by Macbeth followed by Julius Caesar, then that's what will end up at the end here will be the search results, the list of search results with Hamlet followed by Macbeth followed by Julius Caesar. Okay, so that was processString. Let's take a look now at parallel or processInput. This takes an input string, this takes a given work of Shakespeare, and then searches for the phrases in parallel. And so you can see here that we're going to convert the collection to a parallel stream, which is a substring with chunks of phrases, and then we're going to output the stream of phrases to find. For every phrase, we're going to go search the string for that phrase. Now keep in mind that that's all taking place in parallel. So for a given string, for a given work of Shakespeare, we're going to look up the phrases in that string in parallel. And what that means is we're going to go ahead and create a task, or the streams framework will create a task that will call this behavior, this search for phrase behavior, in parallel. And so that will be added to the list of tasks that's being processed automatically by the underlying fork-join framework, the common fork-join pool that's used to run this parallel stream. So we're searching for all these things in parallel. That'll output a stream of search results. And now, because a lot of these things may be empty, we're going to filter everything. So we're going to get rid of anything that is empty. We're going to only filter things. We're only going to let things through the filter that were not empty. And so we'll end up removing the empty search results from the substreams, which also runs in parallel. So we'll end up probably with a greatly reduced set of results. Those are going to be collected. That triggers the intermediate operation processing, and we collect everything into a list. So we end up with a list of search results for all those phrases for that particular input string, and that's what comes back as the result from processInput. And then, of course, as we saw before, processStream is going to create a list of all these lists of search results. So the final result here will be a list of lists of search results. Now, once again, just to underscore a really important point, when I describe this stuff, I often make it sound like it kind of does everything from left to right at one level, and then it does everything from left to right at one level, and then it does everything from left to right at the next level. That's conceptually how it works, but under the hood, it doesn't work like that at all. Instead, these threads are pulling the data from the source through the processing modules, and then the collector is plopping them into the right place in the final collected or reduced result that's coming back. Okay, now that we've kind of seen how to visualize it, the code is absolutely trivial to understand, I think, more trivial. And the most important thing to notice here is that we only have to make minuscule changes based on what we used to have for the sequential version. So you can see here that we have a parallel stream, not a stream. And what that does is that uses the array list splitterator. So we have this call up here, get input, will give us back an array list of character sequences or strings. And so parallel stream is going to go ahead and use the ArrayList split iterator to make a parallel stream that will be used to search the lists of input strings in parallel on multiple cores. So it's going to chop this stuff up, and then each of the slices that are created by the ArrayList split iterator will be fed to the fork join pool and used to run in parallel. This goes ahead and takes a given input string, like Hamlet, and it calls processInput on it, which will then find all the phrases in that. We'll look at that in a second. Allison. Yeah. Oh, yeah, sure. Yeah, great question. So the difference is, the question was, how do parallel and sequential differ if they're being pulled through one at a time? The difference is that for sequential, there'd only be one thread, and it would just start here, and it would pull the first thing through. And then we'd go there, and it would pull the next thing through. And then it would go there, and it would pull the next thing through, sort of from left to right. One thread of control, only one thing happening. With a parallel version, and I only show you sort of a little bit of the decomposition here. I kind of break it up into two chunks. Assume for sake of argument that at any given point in time, we now have two threads. Well, these two threads will be pulling stuff from wherever the starting point is in parallel. So remember what a split iterator does? Remember a split iterator takes a big collection and it splits it up. And with the one we're talking about here, it'll eventually split it up into elements of size 1. So we'll end up, let's say that we have 6 works of Shakespeare, or better yet, we have 37 plays in Shakespeare. So we're going to have 37 chunks that are broken up by the split iterator. Each of those chunks will be handed off to the fork join pool. The fork join pool, let's say it has 4 threads in it. Each of those 4 threads, worker threads, will take one of those tasks corresponding to a single work of Shakespeare, and n of them, let's say 4 of them will run in parallel. So 4 of these things will start from whichever element we have in the input collection that particular split task cares about, and all those 4 things will run at the same time. So think of it like, let's say you go to the laundromat because you have lots of clothes to wash. So if you only had one washer and lots of bags of clothes, you would have to put some clothes in the washer, wash them. When it's done, take it out, take the next bag of clothes, put it in, wash it, take it out, and so on. But if you had n washers, you could load up all your bags of clothes into all the washers, and they'd all start to run in parallel. So that's what's going on here. We're running all of these things in parallel, and each of them is handling a different element in the input source, in the array list, and so they're all able to run in an embarrassingly parallel way, each of them pulling that data element that it cares about through all the processing modules. So that's how you get the speed up. It's by having everything running in parallel, each one pulling the data source through all the different stages in the processing pipeline. Okay, so processInput searches a given input string to locate all the occurrences of the phrase. And what that does is that's going to, what we're going to do here is we're going to have the input strings, right, which we get from getInput. And each of those things is going to be processed in parallel. So the input strings are processed in parallel. Chunks of the input, this is what we were just talking about. Chunks of the input strings are processed in parallel on the common fork join pool. When collect is hit, it triggers the intermediate processing, and it merges everything back into a single list of lists. And you can see here that the toList operation, this is shorthand for collectors.toList, that returns a so-called non-concurrent collector that obeys encounter order. And that's just because that's the way that lists are defined. They obey the encounter order. Collectors on lists obey the encounter order. All right, so that was processStream. processInput is a little bit more complicated because it's got a bit more to do, and we're also setting the stage for an even cooler version of this stuff that we'll talk about later. Probably won't get there today. And so here's what this does. This also, for the purposes of our discussion, is really almost identical to what we saw before. The only difference is instead of saying stream, it says parallel stream. And what that means is it's creating a parallel stream that'll search the input, a given input string, like Hamlet. It'll search that input string to find all the phrases in parallel. So now we're doing the phrases in parallel. So what happens here is map is called. For each phrase, we're going to call map. And map, being a higher order function, we'll call the search for phrase lambda expression, which will take the phrase. Let's say we have 10 phrases we're looking for. Each of those phrases will run in parallel, searching the input string in order to see if there's a match or not. And in this particular case, the splitterator that we're using to do this will be a sequential splitterator. I'll talk about that a little later when we talk about the splitterator that's used to implement search for phrase. I talked a bit about this earlier when we were talking about the sequential version, and we had the try advanced method, which was doing things in an iterative way, and that's the same way it's going to work for now. Okay, so splitterator is used to split things up, and what that means is that all the phrases are essentially tossed into the fork join pool as well. So now we've got a fork join pool that contains a bunch of strings that we're searching as tasks to search, and now we've got more stuff in the fork join pool that corresponds to the phrases as well. So phrases and strings are all running in parallel as tasks in the common fork join pool. But you'll notice that you don't have to write these tasks anywhere. It's only the implementation of the streams framework that's doing all this stuff under the hood through the magic of splitterators. So it's splitting this stuff for you on your behalf without you having to do any of the splitting yourself. Unlike what you had to do for assignment 2, where you have to do the splitting. Whoa, what's going on? And then when we're done here, we go ahead and collect everything together, and that triggers the intermediate processing and merges all the results into a single list of search results, which are then returned. Okay, so that's an overview of how that program works.